And here we have the fly-by-wire principle. It's a very simple principle, but it works fantastically. We get the pilot through this side stick, puts an electrical command into the flight control computer. Now, we're only showing one flight control computer just to keep this simple, but the command is going to all the flight control computers, and they will talk to each other, okay, and determine then a command signal to the servo control. All right. The servo control, what we have on the Airbus is on fly-by-wire aircraft is um, a servo control with a EHSV, electrohydraulic shutoff valve, which basically means I supply a solenoid which enables more or less hydraulic pressure to be able to move this actuator depending on what the electrical supply was. Okay, so the electrical supply is proportional to how much, basically a voltage to hydraulic flow supply to move the actuator. So an electrical signal that's proportionate to actual movement here of a piston, which is aided through hydraulic pressure. Okay, now how much that piston has moved is fed back via an electrical signal to the flight control computer. And when the difference between command and the present position is a null, is net zero, then the electrical signal then stops the signal because we've achieved what we've designed, what we've started off with. That's it. That's the whole fly-by-wire in one little thing. Okay, electrical signal to a flight control computer with an electrical signal to a servo control to mechanically operate a flight control. And here we have the flight control architecture of the A320, which again, 45 years of technology this is. It was unbelievable when it first came out. The way they indicate these boxes, the colors indicate that the brown ones are boxes that are directly related to the ATA chapter 27, flight controls. And the green boxes they're indirectly related to chapter 27 in this case. Okay, so we saw the flight management guidance computers, FMGCs 1 and 2 last session because they were exclusively responsible for calculating the electrical inputs that were going into the flight augmentation computers, okay, and the flight control computers here to be able to move the flight controls when the automatic pilot was flying the aircraft. And similarly, if the human pilot is flying the aircraft, we have the same inputs, okay, going into the flight control computers so that the human pilot can fly, okay, the aircraft, move the flight controls depending on the electrical inputs that he or she is putting in. Now, because there's five flight control computers, all the signals, the summations, and all the calculations and everything is put into two dedicated, they're called flight controlled data concentrators. Okay. They take all the electrical inputs and concentrate them, and they then make the calculations on how much displacement, mechanical displacement on the actuator should correspond to whatever the electrical inputs, together with the attitude, the altitude, the external factors, wind shear, all of the factors to be able to fly the aircraft, either the human or the automatic pilot, in a normal fashion. I also have two computers dedicated for the slats and flap control, for the flaps and the slats. They're called the flap control computers, two of them. Again, only one is in control at any given time to operate the flaps and the slats when called upon to move. Same with the FAC, the flight augmentation computer. Only one is in operation at any given time. The other one is in hot standby. However, in terms of the other flight control computers, these are all working all the time, but with heavy redundancy. There's heavy duplication and redundancy, so that even if one box died, the other four boxes can take over safe operation of the aircraft. And you'll see what I mean now here. So here are, this is, so I once saw in a course, I can't remember where I saw it, but they actually mathematically showed how reliable what the possibility of a total flight control failure would be if you lost hydraulic supply and the computer and the standby computer and the standby computer and the standby hydraulic supply. And it was 10 to the minus 28. The possibility of absolutely losing a flight control computer because it's got so much redundancy. I'll explain. So here, this is the left-hand aileron. The left-hand aileron has two actuators. One operated by the blue hydraulic system, and one operated by the green hydraulic system at any given time. Okay, so that means if I lost the blue hydraulics, the green hydraulics would be able to operate the aileron. Same with the opposite one. Okay. Now you're going to say, hang on a minute. What if I lost blue and green? Yes, if I lost blue and green, I would be able to control the aircraft with the spoilers, the yellow operative spoilers, because when I command the aircraft to roll, that wing down side, the spoilers will activate because the computers will compensate for the loss of the actuation of the aileron, and I've got two yellow spoilers that will do that job. Okay, so there's redundancy there. Now, each flight control has a computer responsible for it. Some have multiple computers responsible for them. Okay, so this one, left-hand aileron, ELAC 1 is responsible for the left-hand aileron. If I lost ELAC 1, then ELAC 2 would control the left-hand spoiler. So all the mathematical calculations, the left-hand aileron. So all the mathematical calculations would be made now by ELAC 2. Okay? The spoilers are pretty dumb. They just deploy and retract. So each one of these has a spoiler elevator computer, a SEC, responsible for one of it. But what's brilliant is that each side has its mirror image, which is supplied by the same hydraulic supply and by the same flight control computer. So that if I lost SEC 2, for example, I would only lose the control of spoiler number 5 each side. Okay, because that's the only one being supplied by SEC 2 or being operated by SEC 2. All right, etc., etc. Look at this. This is the elevator. The elevator has a common blue hydraulic actuator. Okay, and then The left-hand elevator side is supplied by green hydraulics, and the right hand is supplied by yellow hydraulics. So even if I lost the blue, I'd have the green and the yellow supplying both sides of the elevator. And look at the redundancy in the computers. So ELAC 2, okay, is responsible for the elevator, for the left-hand elevator. If ELAC 2 drops out, ELAC 1 takes over. If ELAC 1 drops out, SEC 2 takes over. If SEC 2 drops out, SEC 1. Can you imagine how much redundancy that you have to have 4 computer failures? Okay, you have to have 4 computer failures in one hit for the elevator not to be able to work. These computers, they have a failure once every 6 months. Now you're expecting 4 to drop out in one go, in one event. Never, ever, ever, ever going to happen. Okay, so again, go through it in your if you want to watch this video again and have a look at all the redundancies and look at it. The rudder has 3 hydraulic supplies. 3 hydraulic supplies, and responsible for the rudder is the FAC 1 and FAC 2 for turn coordination. Okay, so there's enormous possibilities here to be able to operate the aircraft safely.